Thank you very much, Ahmed, and thanks to all the organizers of this very interesting conference, the first international conference on sustainable energy systems. My talk will be on two-dimensional materials, design of these two-dimensional materials using first principle approach, including also molecular dynamic and Monte Carlo kinetic. After that, I will give some application of these 2D materials for energy, especially for energy storage, and I will focus on the storage of hydrogen as energy carrier. And this storage will be essentially based on material, on 2D material. 2D materials, storage for 2D materials is adsorbent storage. So first I will give for the two-dimensional materials some brief history and then some properties of two-dimensional material. I don't, okay. Maybe I can move this. Okay, the 2D materials are related to quantum confinement. That means that the charge carrier are confined in one direction and might move in 2 dimensions. And the first example of that has been observed for quantum wells in 1960, in which electrons are confined in one direction while allowing movement within the plane, 2D-dimensional plane. And many interesting applications emerged from quantum wells for lasers, for light-emitting diode, for high electron mobility transistor, for quantum LED light-emitting diode screen, and presently also for quantum computing, which is the actual challenge for the transition of computing. And for this, you can see all the density of state is given by the Heaviside function. 20 years after, these quantum confinements give also another example of two-dimensional systems, which are two-dimensional electron gas. In this case, there is confinement in the interface inside heterostructure. For example, two semiconductor, gallium arsenide and aluminum gallium arsenide. The interface between these two semiconductor exhibit a two-dimensional confinement. In the many applications for that, high electron mobility transistor, and quantum Hall effect. And in the magnetic electric field perpendicular to this 2D electron gaze, the electron adopt quantized cyclotron orbit with Landau level and also with cyclotron frequency. After these two examples, the first truly two-dimensional material has been obtained within graphene in 2004. Graphene is a single layer of carbon atom where electrons behave as Dirac fermion. This discovery revolutionized electronics, but also advanced material, leading to numerous applications. If we consider the simplest model to describe graphene, which is tight bending model with the ion atom energy and hopping transfer between atoms, we can see that in the first Brillouin zone, near the K and K prime point, this model can be simplified to Dirac-like Hamiltonian with pseudo spin Pauli matrix and with very high Fermi velocity and linear energy dispersion. This was the beginning of a very speed and very important area of 2D dimension. And many other studies have been done to look for other 2D dimension. Among these, the transition metal decalcogenide discovered in 2011, like molybdenum sulfide or tungsten sulfide with strong electronic confinement, and many applications also for this transition metal decalcogenide application, nanoelectronic and optoelectronic, flexible electronic, sensor and photonics. And also here, if we consider the simplest way to describe the system using tight bending Hamiltonian with hopping and ion atom energy, and also taking account of the spin orbit coupling due to the presence of transition metal in this component, then we have the low energy effective Hamiltonian near the K and K prime point in the first Brillouin zone as a massive Dirac Hamiltonian with the term of band gap and also terms of spin orbit coupling at the edge of valence and the edge of conduction in the band. And in this case, the energy dispersion is no more linear, but it is non-linear behavior of energy. And the band gap can be corrected by taking into account spin orbit coupling. 4 years after phosphorine has been discovered, very interesting material, phosphorine, is a monolayer of phosphorus, and it is obtained from black phosphorus, exhibiting transparent isotropy with high electron mobility in one direction. Electronic and optoelectronic field and optoelectronic are field of application of phosphorine, and field effect transistor also. I will give some example of the use of this 2D material, phosphorine, for the storage of energy, but for battery and also for material-based hydrogen storage. The simplest way to describe this material is also by tight bending Hamiltonian. In this case, our atom energy and hopping term are present in this Hamiltonian, and we can also simplify this Hamiltonian by introducing effective mass Dirac Hamiltonian with the gap term. In this case, the optical gap is no more zero like for graphene, but it is a semiconductor, and the gap increase with decreasing the number of layers in the thin films phosphorine. I go back to the graphene, the first truly two-dimensional material. It is obtained from graphite, which is a layered bulk materials. The distance between layers is enough to have van der Waals interaction, and the bending energy is low. That means that it is easy to exfoliate one monolayer, which is the graphene. And the structure of graphene is hexagonal one, obtained by some simple mechanical exfoliation. But at larger scale, graphene has some replace. This is to enhance its stability. This material has been obtained, as I show experimentally, but has been studied extensively, theoretically and numerically, and many important and unique property has been shown. For the first thing is that graphene is the strongest known material, harder than diamond, more elastic than rubber, tougher than steel, lighter than aluminum, high electron mobility 100 times faster than silicon, heat conductivity two times better than diamond, and also high surface area, more than 2,600 square meters per gram. The theoretical study show that this material exhibit Dirac cone, and also the linear dispersion energy and gapless, and also this result obtained theoretically has been also observed experimentally by the linear behavior by measurement of ARPES. So this material is very important, and it launched the study of 2D dimension because of its unique properties. And as as a result of this successful development of graphene, many other material has been studied, covering a large range of materials from insulator like boron nitride that absorb light in the UV light to some semiconductor like molybdenum disulfide or phosphorine that absorb visible light to graphene. But even metals have been observed like at 2 dimension, like vanadium dioxide and half metal, which is very interesting, very important materials for the spintronics, like chromium dioxide or chromium sulfide. Even superconductor have been obtained for two-dimensional material like niobium diselenide, and thus show that two-dimensional material can cover a large range of application from insulator to semiconductor, half metal, semi-metal, metal, and superconductor. How to obtain these 2D materials? The easy way to do that is to look for the material, the bulk material with layered structure. And doing some calculation by machine learning, we can see that there is a lot of possible 2D materials obtained from the three-dimensional layered materials. How to do that? First, we have to look for material in the database that have a sufficient distance between layers. And the second criterion is to have a low bending energy. And the third is to show that with increasing the energy needed to increase the distance between layers is not so high. And as it's shown here, you see that carbon distance between layer for the carbon in the graphene can increase by more than 55% with a low energy bending. That means that it is easy to exfoliate one monolayer of carbon from a graphite, that is the graphene. But it is not the unique case. Boron nitride also show the possibility to increase the distance between layers more than 45% with low energy bending. So, in this case, it is possible to have many two-dimensional material easy to exfoliate, and their number, as you see here, is more than 390 if we increase the number of atoms and for binary component. But there are other 2D material that can be obtained by exfoliation from bulk layered materials, but more hardly, and they are called potential 2D material like phosphorine can increase the distance between layers by more than 38%, but that need more energy to do that. And some other bulk iron material can give hardly 2D material. So with that, we can see that there is a lot of possible application for 2D materials, for flexible display touch panel, for transistor with high speed, for conductive ink, for chemical sensor, for light emitting diode, even for automobile airplane component. But in this presentation, I will focus on energy and especially on the storage of hydrogen, material-based hydrogen storage, and also I will give some example of 2D material for batteries. To do that, to design 2D material for this application, we need to make modeling and simulation. Modeling to have a simple model without many parameters, and then to explore the space of parameter by simulation. And there are many ways to do that, and it depends on the length scale and time scale. For short length, angstrom or even nanometer, we need to use quantum mechanics. And quantum mechanics, there are some approaches based on quantum mechanics, like first principle approximation and density functional theory for electronic property. For higher scale, for example, to study atomistic properties, we need to use molecular dynamic. And for micrometers, we can use Monte Carlo simulation, kinetic Monte Carlo or statistical Monte Carlo to study, for example, the behavioral system at finite temperature, for phase transition, for phase stability, and so on. And the engineering is obtaining using finite element approach. The length scale is very important, but time scale is also important to be able to study microscopic process. For example, the time scale for absorption of light and exciton formation is less than femtosecond, from the attosecond to femtosecond. And the excitation dissociation is less than picosecond, while exciton thermalization is of the picosecond, and so on. And for example, for carrier extraction and carrier recombination, the time scale is between microsecond and millisecond. So it's important to know which approach to be used for which design and for which characteristic and properties. In what follow, I will give some detail on first principle methods and density functional theory, and in some result, I will give some result obtained using molecular dynamic and Monte Carlo kinetic, kinetic Monte Carlo. There are several principal approaches for determining the ground state and excited state of many atoms. The first one is quantum chemistry approach, starting from the Hartree-Fock approximation. And this is a time computing consuming, and maybe using density functional theory, which offer an exact background for the many body problem, but can be solved approximately. We can have shorter time of computation. The first principal approach is green function approach on the basis of many body perturbation theory. And if we want to give study like density functional theory, which is an approach for fundamental ground state, for the ground state of the system, but at finite temperature, we have to use quantum Monte Carlo methods. So I start with the first one. As you know, quantum mechanics is based on the Schrödinger equation. And for the quantum chemistry approach, the starting point is the theory is Hartree-Fock. Hartree make the mean field approach, and Fock introduce the exchange. That means that they take into account antisymmetry of the wave function, and the Hamiltonian of this approximation take into account of kinetic energy, interaction between electron and nucleus, and also interaction between electrons. And taking into account this antisymmetry of the wave function as shown by the third term in this Hartree-Fock equation. And we can see that the first, this term is the in-field approximation introduced by Hartree, while this one is due to the antisymmetry introduced by Fock. And the energy it contains the average of kinetic energy and interaction nucleus electron, and this is the Hartree term that contains the in-field approach, and this term is the exchange term introduced by Fock. For the second step, using density functional theory, the functional theory, the density functional theory, give explicit inclusion of electronic structure. And this is very important for many things. First, well, for predictable accuracy, and also because the knowledge of the electronic structure can be used for the analysis, and many observables can be obtained directly for energy and density and correlation and so on. Many other properties can be obtained. And the third and important point for the density functional theory is that it is preferable scaling. We can go for upscale more easily than using quantum chemistry method. This theory is based on three approximations. The first one is the Born-Oppenheimer approximation that neglect the kinetic energy of nucleus and also factorize the wave function of nucleus from that of electrons. And the second point is the Hohenberg-Cohen theorems that introduce two main important theorems for DFT, which are first the density of charge and the how to obtain the energy of the ground state. And all these approximations are introduced in the Cohen-Sham equation, even here. And this equation is looking like single particle Schrödinger equation. It reduces the number of equations from a very, very high number of equations for Schrödinger equation to only a single particle Schrödinger equation. It's a very important approximation done by Cohen-Sham to obtain this equation. This equation is nonlinear, highly nonlinear, but the potential depends on the density as is shown here. It is the Cohen-Sham potential. It contains it depends on the density. It is a local potential. It is exact, but the exchange correlation energy is not known explicitly. If we need to introduce all the exchange in the equation, we can do that, but its evaluation is very time consuming, and often the accuracy is not improved over simple approximation. But the most important point is to solve this equation, we need to make self-consistent solution. And to do that, we need to fix a number of parameters. For the first term, which is the kinetic energy, we have to show what is the nature of electrons. Are they full relativistic or semi-relativistic or non-relativistic? For the second term, which is the potential generated by nucleus, which is called here external potential, we have to choose periodic for crystalline structure and non-periodic for amorphous or disordered system. But we need also to show the nature of the core electron. Are they considering as a pseudo potential or as all electron full potential or hybrid both like projector augmented wave? The third term is the most important in the Cohen-Sham equation because it contains all what is not known in the system, which is exchange and correlation. And for this, many things have to be fixed. First, is our system a magnetic system? In this case, we consider spin polarized or non-magnetic system. And for that, we use non-spin polarized. But the solution depends on the approximation. is the system. If we consider local density homogeneous locally by LDA, we can solve the system, this Hamiltonian. But if in our system there is some variation of density, then we have to use generalized gradient approximation, taking into account this gradient of density in the system. And we can go beyond this simplest approximation by introducing Hubbard coupling, or by introducing quasi-particle, or by introducing time-dependent density functional theory for dynamic, or for some fast dynamic process in our system. The last parameter to fix is the how to represent the wave function. And for that, we have to choose the basis. And there are many ways to do that. Basis as atomic orbitals, or as plane wave, or as augmented plane wave, or as augmented spherical plane wave. All these parameters are needed to make self-consistent solution of Cohen-Sham equation. But I give some example of the method used for some property looked for. For example, for band gap, if we want to determine the band gap of our materials, we can, of course, use Cohen-Sham equation, and many approximations are available. LDA, GGA, modified BG, hybrid, which combine exchange and introduce a part of exchange into the Hartree term, which is mean field term, and also other approximation, and that help to determine the gap which depend on the approximation used. If we are interested by band structure and band offset at interfaces, we have to use excited state method, including JW method based on perturbative expansion of the one particle Green's function. And in this case, the equation is the Dyson equation, in which we have the electronic self-energy, which is the factor of Green function and the screened Coulomb interaction. And the first order expansion, perturbative expansion, is G0, W0. If we are interested by optical spectra and exciton, then we have to use method based on the perturbative expansion of the two particle Green function, especially electron and hole. This equation is Betz-Salpeter equation, and from this equation we can determine the exciton energy and also the exciton wave function and the optical absorption. If we are interested by excited state dynamic, we have to use time-dependent DFT based on the Schrödinger equation, time-dependent. And for fast carrier dynamic, which is a new frontier of first principle calculation with the great potential to impact the PV regions due to the importance of process taking place at femto at nanosecond time for solar cells. we have to use semi-classical Boltzmann transport equation and its quantum version Kadanoff-Bayan equation. Okay, now I will give some example of 2D material using the approach I already have done, including DFT and some also molecular dynamic and Monte Carlo simulation. I start with graphene and show how we can control graphene's properties using some modification and to design new material with new property for some application. And I start with graphene, as I say before, for three type of modification. The first one is passivation. The second one is stacking. And the third one is dapping or substitution. What's that mean? I start with the first case, passivation. We can make passivation of graphene by hydrogen or using fluorine. But with that, we change the properties of graphene from a semi-metal to other phases, for example, to semiconductor. Here, the example of the passivation with hydrogen, and in this case, the atoms of carbon make band with hydrogen, and the tight bending give this Hamiltonian to describe, and we see that the band structure change from the gapless to a semiconductor with a gap, direct gap, and no more linear energy dispersion, but with a term, non-linear term of the energy. And this result has been also observed experimentally by the increase of the conductivity as function of temperature, which is characteristic of the semiconductor behavior. So passivation can move the graphene from semi-metal to graphene, which is semiconductor. And the same behavior may be obtained by passivation by fluorine, which move the graphene to fluorographene, which is also a semiconductor. And these results have been also done experimentally with a direct band gap. Second interesting behavior is the stacking. Stacking may mean how the layers of graphene are stacked for bilayer or tri-layer or even for thin films. The stacking, the natural stacking for graphite is EB stacking. That means that the atom of carbon on the first layer is on the top of the hollow of the second layer, as is shown here. This is the EB stacking. But if we make a shift of this layer with respect to another layer, then we can change from EB to EE, where carbon is on the top of carbon, not on the. And what is shown here is the stability. We can see that the most stable configuration is EB, which have the lowest energy. Of course, it depends on the distance between layers. And if the distance between layers increase, then we obtain the behavior of graphene. But if the distance between layers is smaller and it is of the order of the van der Waals interaction, 3.6 angstrom, in this case, the most stable is first EB and then EE, and in between, by in intermediate position, we can see that the stability decreases. But what happened for the band gap? The band gap is 0 for EB, for B layer EB, but if we make a shift, then this band gap will increase to EE, where the materials, the B layer, behave like a semiconductor, while it was for EB, it was semi-metal. And in between, we can see that there is an opening of the gap depending on the shift between the two layers. And for this, we can see that for EE stacking, there is a semiconductor behavior and an increase of the electrical conductivity versus the temperature. This many layers graphene has been observed experimentally, and the characterization using Raman shift show the shift of the peaks depending on the thickness of this layer. So it is important to move from semi-metal to semiconductor by increasing the number of layers from monolayer to few layers. But it has been observed that we can do better than that. We can go with a very small shift by making rotation of 1 degree or 8, very small one. And in this case, with this small angle, with this small twist of a first layer with respect to the second layer, we observe that in this B layer, we observe both the EE and EB in different regions. And in between, there is other angle. So to obtain periodicity, we have to look for moire superlattice vector. And in this case, the moire is 3130 for an angle of 1 degree, 0.8. So in this case, we have gap and gapless at the same time. And as you know, the pseudo gap is a characteristic of superconductor. And this material, B layer of graphene, might exhibit superconductor behavior. And we can see that for the band structure with the flat band. And also, if we look at the Fermi velocity, we can see that it is always the velocity of graphene for for angle of 30 degrees, but for very small degrees, the velocity is very low. And experimental studies have shown that for small angle, this is theoretical value, and this is experimental one, show that this angle, 1.05, there is resistance is zero. That means that superconductor behavior in for low temperature is some degrees. So stacking can change the nature of bilayer graphene from semi-metal to metal, to semi-metal to semiconductor, or to superconductor. Another way to change, and this is very important for battery. As you know, for battery, the anode is made of graphite, many layer of graphene with distance of van der Waals distance. But if we can do that with silicon, it will be very interesting. And silicon have its silicon carbide. This silicon carbide have it is a semiconductor with the gap, the direct gap. So we can go from semi-metal to semiconductor by substitution of 50% of carbon by silicon. And this has been shown theoretically using tight bending approximation, and also by doing experimentally, and show that silicon carbide with 50% on silicon is a semiconductor. But we can do that with small concentration of silicon, 8%, 12%, 25%, and reach 50% at the end. And what it is shown that with that we can change the bend gap depending on the concentration of silicon from 0, which is semi-metal, to 1, 1.3, and at 50%, 2.5. And this is shown by the band structure and density of state. And also we can see this behavior for the absorption, which is graphene do not absorb a lot, but silicon carbide absorb, and with increasing the density, the concentration, we increase the absorption of light by the materials, and also the increase of electrical conductivity versus temperature. Another modification is the geometry of the material. Here is the silicon carbide with 50%, but with tetragonal structure, which means we have two holes, a small one and the big one, and it depends on how the silicon or carbon are positioned on this structure. The behavior change from small band gap to large band gap, and the absorption change, and also the electrical transport property change. For the first one, with the small band gap, we observe first a semiconductor behavior, and then a metallic behavior. A decrease of conductivity is a metallic behavior, while for the second one observes only for the electrical conductivity, only the increase of the electrical conductivity, which is characteristic of the semiconductor. So geometry can change, the property of the material can change by changing the geometry of the same material with the same concentration. Here, another case of that, it has been obtained by 25% of silicon in graphene, and depending on the position of the silicon in the structure, we can have para-silicon carbide or meta-silicon carbide. The first one is semi-metal, while the second one is semiconductor. Semi-metal with a direct cone with linear dispersion energy, and the second one is semiconductor with a direct band gap. But we can modify this property by strain. And by making strain on this para-silicon carbide, we can see that there is a decrease of stability of the materials with increasing the strain, and also a change of the lattice parameter. And this gives transition from a semi-metal to a direct semiconductor for 9% of compressive strain, but over that, below, higher than that, for 10, it's still semiconductor, but it is now an indirect band gap. So we can, as you see, we can change the property of this 2D material by changing the geometry or by making some strain that compressive or tensile strain can change the behavior. And as is shown by the electrical conductivity for the semi-metal, there is a decrease of electrical conductivity with temperature, while with strain it increase that show that it is a semiconductor. A second example I will give for 2D materials is phosphorene. Phosphorene is different from graphene in many ways. First, this material is not semi-metal, it is a semiconductor. This material is not a flat hexagonal, but puckered hexagonal with two levels. This material is not isotropic like graphene, but it is anisotropic with two directions, armchair and zigzag, and many other different applications. And for that, the application of phosphorene are for different area than that of graphene, but are 2D materials. This material has been obtained in the same way as graphene by exfoliation, but to make exfoliation, we need to look for a layered bulk material. And the layered bulk material for phosphorus is the black phosphorus. As is shown here by Sim, this is a layer of black phosphorus. And this material is obtained from the red phosphorus, which is less stable than the black one, using a chemical vapor transport deposition. And the EDX show that there is only phosphorus, no other element here. And the characterization using X-ray diffraction and Raman show that it is really hexagonal structure with a layered configuration. And to obtain monolayer, two-dimensional phosphorene from these bulk layered materials, we make exfoliation, solvent exfoliation. The solvent used here is NMP, is organic solvent, and with some sonication and some centrifugation, we can separate different thickness of these materials, phosphorene, few layer to some layer, and even one monolayer, as shown by high resolution TEM. Okay, these are how this material has been obtained experimentally. But theoretically, using density functional theory, the obtained results confirm what has been observed experimentally and go beyond. First, it shows that the hexagonal structure is stable one, and it is anisotropic with two directions, armchair and a zigzag direction. It shows that it is a semiconductor with a direct band gap, and the optical gap obtained theoretically show that for a monolayer of puckered phosphorene, the band gap is 2 electron volt. Many other results have been obtained by using density functional theory. The effective mass of electron and hole has been calculated, the mobility also, and it has been shown that there is a high carrier mobility with asymmetric mobility. That means that electron and hole do not have the same mobility, and also anisotropic property. That means that the mobility in the armchair direction and in the zigzag direction are different. And for that, the dominant mobility for this material is that of hole along the zigzag direction. And also the absorption of this material has been studied. So using density functional theory, it's possible to study in deep the property of this 2D material. However, there is a lack in this material there back, which is it is not stable. It's not very stable, and we have to make some modification to increase its stability for some application. Phosphorine is unstable in an environmental with hydrogen, not with oxygen and water. And to show how come this instability, we have to look for the adsorption of hydrogen and water on the surface of this material. Okay, there are many sites for adsorption of oxygen molecule or water molecule. On the top of phosphorus or on the bottom, on the bridge between two phosphorus. There are two bridges, one on the top and the other one at the bottom, or on the hollow between phosphorus. What is the DFT calculation show that the most stable adsorption is that of hydrogen, oxygen on the top, more than the energy, bending energy of water. That means that degradation came from the oxygen, the adsorption of oxygen on the surface. And after the most stable is on the top of phosphorus, and then on the bridge at the bottom, and then on the hollow. But this adsorption change the behavior of the density of state with oxygen on state of oxygen on the band gap. And we can also observe a charge transfer from the phosphorus to the oxygen. But to look for stability, we have to do molecular dynamic and to see if this this adsorption go to bond between oxygen and phosphorus. And using molecular dynamic with 5 picoseconds at room temperature, we can see that oxygen adsorb on the surface and make a bond between phosphorus and oxygen. And this is the first responsibility of the first origin of this degradation of the phosphorus in presence of oxygen. But if we look for the black phosphorus, we see the same behavior for the black phosphorus for many layers of phosphorine. We can see that with increasing the time during the simulation, that oxygen make band with phosphorine and penetrate deep in the black phosphorus. That means that the material is not stable. This material is not stable by in presence of oxygen. And how to make it more stable? We can do that by some decoration with fluorine. We make some fluorine atom on the surface of the phosphorine to make some passivation, and then look for the effect of oxygen or water on the surface of phosphorine phosphorine with fluorine. By increasing the number of fluorine on the surface surface of phosphorin, we see that it is the most stable configuration is with 25% of fluorine on the surface of phosphorin. It's the most stable adsorption of fluorine on the phosphorin. So we consider this concentration and look for the stability of the material using molecular dynamic. We see that the band gaps still have semiconductor behavior with the opening gap, and molecular dynamic show the stability of this phosphorin with 25% of fluorine on the surface, that it is stable at room temperature. It is stable, but did it protect the phosphorin from oxygen and water? We see that with respect to what has been shown earlier, the adsorption of oxygen have very low value, and even water have low value compared to without fluorine, and the diffusion barrier is very high for electron volt for the oxygen and for more than 4 electron volt for the water. That means it is not easy to move on the surface of the phosphorin. And with that, if we look for the stability of the material, we can see that using dynamic molecular, oxygen molecule do not penetrate into the phosphorin. Phosphorin with fluorine is protected even after many time. And the same thing for water, the second figure, this one. It is stable at room temperature, and no big interaction between water and phosphorin. And even if we take both water and oxygen, there is no big interaction and no degradation of phosphorin when it is passivated with fluorine, while it is always semiconductor. How we can, I show that it is stable. We can make it stable, phosphorin, we can make it stable by some passivation with fluorine, but we can also change its properties by making some modification. Here, after I will show 4 cases. The first one is the effect of thickness, how the properties of phosphorin change with thickness, and then how this property change with strain, and then with stacking, and at the end for heterostructure. This is the, without the modification, calculated using density functional theory. Very important property for phosphorin. First, high crystallinity, high surface area, very useful for adsorption and also for photocatalysis, 800 square meter per gram. It is absorb visible light, very important for photocatalysis. mechanical strength, light transmission, and also charge mobility, good charge mobility, 1000 square centimeter per volt and second. How to change these properties? We can improve only by making some thickness effect. That means we increase the thickness of the materials. The bulk phosphorus, the black phosphorus, bulk one, is a semiconductor, but a small gap, 0.3. And the monolayer, as you see here, is 2 electron volt. By increasing the number of layers from 1 monolayer to B layer, 3 layer, and so on, what happens is decrease of the band gap. This decrease of the band gap means the possibility of turning the absorbing light to choose the best light to absorb. And this thickness change also the work function. This is useful for the charge transfer and also change of the effective mass for hole and all electron in both direction, armchair and zigzag direction. And this is responsible of the mobility. For that, I say before that the mobility is higher for holes in the armchair direction, and we can control this mobility by increasing the number of layers. This is the first effect to change the properties of phosphorus. We can change also the property by strain engineering. All these results are obtained using density functional theory. We can also change the property by using strain engineering. As you see, without strain, we have a gap, but we can increase this gap by some tensile strain or decrease it by compressive strain. And at the same time, if we increase more, we can change the behavior from direct band gap to indirect band gap. So we can turn the band gap by making strain. Strain, as you know, phosphorus is a 2D material, and if we put it on a substrate, the mismatch between lattice parameter can make some tensile or compressive strain depending on the mismatch between the lattice parameter. So the second way to modify phosphorus is using strain. The third one is stacking, like for graphene. Here also, the most stable stacking is that of black phosphorus, which is EB staking. But there are many other possibilities for staking layers of phosphorus. This to change the stacking, it's easy to do that by some intercalation of ion between the layers. By this intercalation, we can change the stacking from EB, the most stable, to EC, ED, but all this stacking, phosphorine stacking, are stable with, but with different band gap. Then it is possible to control the band gap by making stacking, changing the stacking. For the application of this material for photocatalysis, for example, it is possible to move the alignment of the band by controlling acidity of the solution in which we put this material, by controlling the pH effect. And for example, in this case, for 8, for phosphorine, pH equal 8, we have possibility to have at the same time oxidation of water and a reduction of proton. In the third part of this presentation, I will give some application of 2D materials, and I give some example for energy storage, especially hydrogen storage, material-based hydrogen storage, and some example for lithium-ion or sodium-ion battery for 2D materials. It starts by material for hydrogen storage. Here briefly, value chain for the hydrogen and the key technology for hydrogen. There are 5 important technology for the hydrogen as energy carrier. First, its production, then its storage, delivery, and conversion, and at the end, application. As you know, for the production, there are many ways to do that. I will not give example of material for that, but I recall briefly that at near term, there is a need to produce hydrogen without the emission of carbon dioxide, and this hydrogen is what is called blue one. It can be obtained by gasification of coal or biomass and waste with carbon capture, or by advanced fossil and biomass reforming conversion. But the most used actually is electrolysis. If the electricity is renewable from wind or from solar, then it is the green one. And the future is to use, at middle term, to use biological or microbiological conversion. And for longer term, the term one, photoelectrochemical water splitting. And Professor Nawi will speak in his tutorial about this long-term evolution. Even the near term also for electrolysis, but also for photoelectrochemical water splitting. Here I will go to the storage. I will give example for the storage. Now, near-term storage as a gas, it need a high pressure, or as a liquid that need very low temperature, minus 250 degrees C. At middle term, geological storage, salt, cavern salts, or depleted oil gas reservoir, but also combining cryo and compression. and also chemical hydrogen carrier like ammonia or methanol. But it is the long-term way to store hydrogen is material-based hydrogen storage. And that means that hydrogen will be stored in a material, in a solid material. And this storage depends on the nature of the material. It can be storage in a chemical way, chemical hydrogen, like water, or complex hydrogen. Why complex? Because it's hard to desorb hydrogen from this material, because that need two reaction of desorption. And the interstitial hydride, like magnesium hydride, the most advanced material for hydrogen storage, or in a liquid, organic liquid. But the last way to do that is the adsorbent. That means that the hydrogen will be stored at the surface of the materials. And this is good for 2D materials and also for metal organic framework. So in this presentation, I will give some example on the adsorption of hydrogen on 2D materials. At first, I give the criteria for a good tank for hydrogen storage. First, appropriate thermodynamic. That means that the energy needed to desorb hydrogen from the materials or from the tanks, that must be around the room temperature, not very high. And the second criteria, fast kinetic. That means quick uptake and release of hydrogen from the tank and into the tank. And the third, high storage capacity. That means that this tank must be not very heavy and not very big, not a great volume, small volume and small weight. And also long cycle lifetime for hydrogen absorption and desorption. Okay, many material has been studied for that, from water with more than 1,900 to desorb temperature, to desorb the hydrogen, to the mouth of very low temperature. But in between, many other material has been studied with decreasing desorption temperature, the temperature needed to desorb hydrogen from the material. And the most studied is the magnesium hydride, this one. Okay, I give briefly some results concerning this material, and I go to 2D material based on magnesium hydride. Magnesium hydride have uptake of 7.6 weight percent, very good value compared to the norm, which is less than 6. And the volumetric capacity, very good, 110 grams of hydrogen per liter, and it is higher than the norm. But two disadvantages of this material. The kinetic is low, and the temperature of reaction is high. And there is a need to reduce both the kinetic, reduce the kinetic, and improve the kinetic, reduce the time of absorption and desorption, and reduce the temperature of desorption. And this has been done using density functional theory, and it has been shown that by making some substitution of magnesium by other element like chromium, for example, the gravimetry still high, but the desorption temperature is around the room temperature. We can even improve the gravimetry by making some substitution by light element like bar or lithium. And in this case, we can increase at the same time the gravimetry and reduce the desorption temperature. This result has been also observed experimentally obtained with some substitution. It is possible to reduce the desorption temperature and also it is possible to improve the kinetic. And this study has been done using kinetic Monte Carlo simulation by calculating the best position for the adsorption of hydrogen first, and then by calculating the activation energy, which means the barrier diffusion barrier. And it has been shown that the best substitution is with nickel, decrease the time of absorption and desorption, as is shown here. Time of absorption decreases with the substitution of only few percent of magnesium by nickel, 8%, and the same thing for the time for the desorption of hydrogen. And these results have been obtained experimentally. Now I go back to the two-dimensional for this material. This material have a high desorption temperature for the bulk. You see that this is the temperature, more than 500 for the bulk. But by decreasing the thickness of the film to monolayer or few layer, the desorption temperature decreases from 500 to 300 H. And we can also decrease more the desorption temperature by making some substitution in this 2D material. By substitution of magnesium by aluminum or chromium or niobium, etc., we can reduce the desorption temperature. It is also possible to, like I show here, possible to reduce the desorption temperature by making some strain, tensile strain or compressive strain, and the desorption temperature go from 380 to 260 or 250 for tensile and 260 for the compressive. So the magnesium hydride is a good material for hydrogen adsorption, for hydrogen storage, but we can enhance the property of this material as material for hydrogen storage by making a two-dimensional material as shown here. By increasing the thickness, the performance decreases, but the best one is with monolayer And also we can improve the result by some substitution or some strain for both. And the effect of size and dimension has been also studied experimentally. And it has been shown experimentally that with one dimension we can reduce the desorption temperature.
Professor, you have still 5 minutes.
Okay. And increase the desorption and improve the stability. And at the same time, we can improve the time of absorption and desorption of the hydrogen from this material. I will end with this example. I go back to the phosphorene. As I said before, it is obtained from layered black phosphorus and using exfoliation in a solvent with sonication and centrifugation. And this material can be used for hydrogen storage. And it gives very good value for the desorption temperature, which is around the room temperature. And the gravimetry is more than 4 weight %, and it can be improved by some modification. Here, how this has been done using density functional theory. The first step is to look for the most stable position for hydrogen molecule on the top, on the top of the phosphorus, or on the hollow, or on the bridge. And it has been shown that the best one, the hydrogen preferred to be adsorbed on the middle point of the bottom phosphorus-phosphorus bond, which is the molecular axis perpendicular to the phosphorus. And with that, the kinetic is also good because the diffusion barrier is lower than that of the graphene. For example, for graphene, the diffusion barrier is 14 millielectron volt, while for phosphorus is only the best one is 0.3 millielectron volt. So this material is good for the storage because of low desorption temperature and very good kinetic. With that, I end this talk, and I will give a summary in which I tell that 2D material are new material discovered in 2004, but with the big speed and evolution with many other 2D material that cover a large domain of nature of material, but also of application. It covers a large scale of application, including energy. And here I give some example of hydrogen storage as application. The same material can be also used as electrode, anode or cathode for battery, lithium or sodium ion battery. Thank you for your attention.